Empirical parameters are not universal constants in an absolute sense. They encode the context in which they were measured. When you calibrate a theory in a specific environment, its parameters absorb the structure and constraints of that environment. They act as a compressed fingerprint of a given complexity level. When you move the theory to a different context, that compression breaks. Errors appear and grow with the mismatch. This is not a failure of the theory. It is a consequence of applying a context-bound description outside its domain. The hydrogen atom is a minimal system. It is effectively a two-body problem with strong symmetry. A small set of constants gives precise predictions. This works because the system has reduced degrees of freedom. When you move to a diatomic molecule, that simplicity disappears. You now have coupled motion, geometry, and electronic structure. The hydrogen model no longer suffices. You must introduce additional parameters and effective descriptions. Each new parameter encodes information that could not fit into the simpler context. Newtonian gravity solves the two-body problem exactly. Motion stays in a plane, and a single constant g defines the interaction. This is a low-complexity closure. Once you introduce a third body, the system loses integrability. There is no general solution. To model real systems like the solar system, you must add corrections, approximations, and fitted parameters. The constant g remains, but it no longer carries the full description. The system requires more structure than a single parameter can encode. At galactic scales, the gap becomes clear. Observed rotation curves do not match simple gravitational predictions based on visible matter. One approach adds fictional dark matter, with a distribution tuned for each galaxy. This increases the number of parameters. Another approach, MOND, introduces a single acceleration scale, A0, that captures a transition in behavior. From a parameter perspective, the contrast is direct. One framework spreads complexity across many fitted components. The other compresses it into a single scale, tied to a specific regime. The same pattern appears in machine learning. A model trained on a narrow domain performs well because its parameters encode a stable context. When you expand the domain, errors appear. The model produces inconsistent or incorrect outputs. These are not random failures. They reflect a mismatch between the learned context and the new one. To reduce these errors, you increase the number of parameters and training diversity. The model must encode a broader range of structures to remain accurate. Parameters do not exist in isolation. They are tied to the context in which they were measured. Their stability reflects stable environments, not universal validity. When context changes, you must either accept error, introduce new parameters, or change the level of description. This applies across physics and artificial systems. Complexity limits compression. Every parameter is a trace of the environment that produced it.